Hello there. So let's look at equilibrium now and using Le Chatelier's principle to modify and manipulate a reversible reaction. So let's think about an example first. Of course, we normally read a chemical equation from left to right, what we'd refer to as the forward reaction. In this case, using up dinitrogen tetroxide and producing nitrogen dioxide. The dinitrogen tetroxide we start with is colourless. The nitrogen dioxide is a red-brown colour. So as that red-brown colour appears, we know we're producing nitrogen dioxide in the forward reaction. However, there's a competing back reaction that uses up our product, now thought of as the reactant, nitrogen dioxide, and converts it back into the dinitrogen tetroxide. So as that orange to brown colour disappears, we're using up this chemical to drive the back reaction and reproduce our original starting reagents. So our reaction is actually a two-way street. Dinitrogen tetroxide being turned into nitrogen dioxide, and nitrogen dioxide being turned back into dinitrogen tetroxide. A two-way street. Let's see how this develops. So we start off with some amount of dinitrogen tetroxide, and as it reacts, we start to use it up so its concentration decreases. We're producing the nitrogen dioxide, so its concentration is increasing. We can see that after time, the concentration of the nitrogen dioxide and the dinitrogen tetroxide eventually levels out and becomes constant. Now, why is this? Well, we look at the rates of the two competing reactions. Of course, we start off with lots of the dinitrogen tetroxide, the N2O4, so with lots of collisions, the rate is high. But we're using it up. The concentration drops, and so the rate of the reaction drops. We're producing nitrogen dioxide, its concentration is increasing, so the rate of the reaction is increasing. But we eventually reach a point where the rate of the forward reaction, N2O4 into NO2, is equal to the rate of the back reaction, NO2 back into N2O4. So when the rates of the two competing reactions becomes equal, the concentration of each chemical no longer changes. We've reached a state of dynamic equilibrium. We're using up one chemical in one reaction as quickly as that chemical is being reproduced in the other competing reaction. So, looking at this example for a little bit longer, let's think about how Le Chatelier's principle applies to this reaction. Remember, we talked about adding chemicals. If you add a chemical, the position of equilibrium moves away from that chemical. You're compensating because you have too much. And so in this case, if we add more N2O4, the position of equilibrium would move to the right, away from the N2O4, and produce more of the product, NO2. On the other hand, if we remove N2O4, the system tries to compensate for losing the N2O4. We say the equilibrium moves towards the chemical. That would favour the back reaction, which moves from right to left, and so we produce more of the product of the back reaction, produce more of the N2O4. We use up a chemical, the system compensates to produce more of that chemical. We could decrease temperature. Remember, a decrease in temperature favours the exothermic reaction, the one that's giving out energy to replace the energy that's been lost by the temperature drop. In this case, it's the back reaction from right to left, which is exothermic, as it gives off energy. So decreasing temperature would cause more of the N2O4 to be produced, along with that energy. And if we decrease pressure, remember a decrease in pressure favours the reaction with the most moles of gas. That would be the forward reaction, turning 1 mole of N2O4 into 2 moles of NO2. 1 becoming 2, the forward reaction would be favoured, and we produce more of the NO2. We compensate for having a larger volume in the reaction when pressure is decreased. Remember the syringe analogy. So let's take a look at the 4 reactions we're going to be studying today. First, we've got the iron nitrate reacting with the potassium thiocyanate to produce this iron thiocyanate complex in the forward reaction. And the back reaction breaks it down back into the original ingredients. The starting iron nitrate is yellow in colour. The product iron thiocyanate is red in colour. Now there's a couple of spectator ions in this. Basically the nitrates are all spectators along with the potassium. So we can look at this equation with just the net reagents, iron thiocyanate and the iron thiocyanate complex. Remember the iron complex is yellow and the iron thiocyanate complex is red. So if the solution becomes more red, it's because we produce more of this complex. That's only produced by the forward reaction. So if the red colour becomes more intense, the forward reaction is favoured. Equilibrium moves to the right. If the red colour disappears, or the reaction becomes more yellow-like in colour or colourless, then the iron thiocyanate complex is being used up to turn into the original potassium thiocyanate and the iron nitrate. The back reaction is being favoured as that red colour disappears. Let's look at experiment number 2. It's the copper hexahydrate, which is blue, turning into the copper chloride pentahydrate, then eventually the copper dichloride dihydrate, and from there the copper trichloride hydrate, and finally the copper tetrachloride. A 5-step reaction for the second system. So we have got different chemicals which will create different colours. Now experimentally the colours look a little bit like this. The blue for the hexahydrate complex here, the light green for the chloride pentahydrate, this dark green for the dichloride dihydrate. It's supposed to be yellow for the trichloride hydrate. I couldn't quite get it to come out, but you can see that it's trying to become less green and more yellow. And then finally, with all the water gone, that copper tetrachloride is a kind of dark orangey colour. So those are the colours you're shooting for the different complexes in this equilibrium system. Now overall for the system, we've got increasing amounts of chloride being added, replacing the water to eventually form this copper tetrachloride complex. So as we add more chloride ions, we move away from the chloride, equilibrium moves further to the right. If we remove the chloride, we compensate for the removal of the chloride and move towards it and move equilibrium further to the left. So add more chloride, we move to the right. Remove chloride, we move to the left. The other big component in this reaction is the water. Now this is true because the water is part of the copper complex, so it's not just being used as solvent. The more water we add, the more equilibrium moves away from it to the left. If we ever remove water, equilibrium moves towards it to the right. With experiment 3, we have got the cobalt hexahydrate, which is pink, turning into the cobalt tetrachloride, which is blue. Similar to the reaction we had in the previous step, where it's driven by chloride and water. So adding chloride, like before, Adding will move away from the chloride and move equilibrium to the right. Removing chloride causes us to compensate and move towards it, move to the left. If we add water, we move away from the water to the left, favouring the back reaction. If we remove water, we compensate for the removal of water and move towards it, move to the right, favouring the forward reaction. Now in this experiment 3, you've also got to think about endothermic and exothermic reactions. Remember, when you put it in the beaker of hot water, you're supplying energy to the reactants, you're increasing temperature, and that always favours the endothermic reaction, because the endothermic reaction will use up that energy to compensate. If you put your test tube in a beaker of cold ice water, that's taking energy away from the reaction. That will favour the exothermic reaction, and look for the colour change as appropriate. That will tell you which of the two reactions is exothermic. Pink to blue is the forward reaction favoured. Blue to pink is the back reaction favoured. Let's take a look at experiment 4 finally. The ammonium chloride dissolving in water to form ammonium ions and chloride ions. Remember, your visual cue here is the appearance or disappearance of the ammonium chloride. If this solid precipitate disappears, it's being used up in the forward reaction. Equilibrium is moving to the right. If the precipitate reappears, it's being produced in the back reaction as equilibrium moves to the left. Remember, if you add water to the reaction, think about how it's going to affect the concentration of those ions in solution. Remember, if the test tube feels cold, it's because the reaction is using up energy to drive one of the two reactions. If the test tube feels hot, it's releasing energy because it's giving out energy as an exothermic reaction. And finally, remember, when you make up that solution, make sure it's absolutely saturated. Make sure it's dissolved all of the ammonium chloride that it can possibly dissolve. So you'll have to keep adding and mix on the vortexer until it stops dissolving. The vortexer works by pressing down on top, as we see here. And finally, all of our waste goes into the inorganic waste bottle, which might be marked as metal ion waste. Good luck, and just ask if you have any problems.